is easy. It's just 1. So now we can replace this with 24 times 6, or divided by 6 times 1, or 24 over 6, which is 4. 4 groups can be chosen. If we're choosing groups of 3, we can have 4 different groups going to the moon. And this is a combination. The binomial probability distribution is a very important mathematical model. It has varying applications all over science, in statistics, mathematics, into biology, into business, all over the place. The binomial is a very, very important distribution. And it's important that we get the hang of it. Now, I've got it written up on the board. I'm going to walk you through it. Then I'm going to tell you when you can use it. Okay? So the binomial, again, is given by a combination. N factorial over x factorial times n minus x factorial times p to the x, 1 minus p to the n minus x. Now, that seems a little bit complicated, but here's the deal. This is what we're doing. We're looking at 2 distinct groups, successes and failures. So, our list has to come from a finite number n. Okay, our sample has to be from a finite number n. N, the number of people in our sample. Then we have to be able to divide our outcomes as successes and failures. And they have to be collectively exhaustive and mutually exclusive, meaning a success cannot be a failure cannot be both a success and a failure. It has to be a distinct break, success and failure. And that has to describe all the outcomes. You can't have success, failure, and maybe. No. You can only have 2 groups. And they have to be collectively exhaustive, meaning they have to be your full list, 2 groups, and they have to be mutually exclusive, meaning they cannot both be a success and a failure at the same time. For instance, if we're looking at cancer research, a success might be a remission, and a failure might be a non-remission. Okay? There are no other options. You're either in remission or you're not. Yes, you're in success or failure. Okay? This is primary to the fact that this is binomial model. Now, you might see bi in the title and understand that it's 2. Bi means 2. Bipeda, humans are bipedal, we have 2 feet. Binomial meaning we have 2 groups, success or failure. So this is your tip-off. Okay? Now, again, we're looking at the probability. Here I have the piece of x. This is the probability of success given n and p. Okay? Given a number n, a fixed number n, and p. Now, this p, one other condition that holds for the binomial is that the probability of the success is constant from observation to observation. Okay? The success does not change, the probability of cancer success rate does not change from patient to patient. Okay? No. It's got to be uniform and constant over the whole sample. Okay? Success probability does not change. If the doctor's treatment of chemo has a 40% chance of success, that's the same 40% chance of success for my family members as it is for your family members, as it is for anybody else who receives that treatment. Therefore, the probability of failure is also constant. So if the probability of success is 40%, we know, because it's 2 groups, that the probability of failure is 60%. And you should be starting to realize those things in your head at this point. Okay? Now, when we have probabilities of success is listed as p. 1 minus p, therefore, is the probability of failure. So, if this is probability of success is 40%, we know 1 minus p, 1 minus 0.4 is 0.6. That's the probability of failure. And x is the number of successes. x is tied to p here. So x is the number of successes. N minus x, therefore, would be the number of failures, right? And so let's think about this. A set number n, right? That means we have to have, say, 4. We have 4 people, and we want to look at 4 people in treatment. We want to look at the probability that one of them goes into remission. Or we could look at, we have 4 people. I want to look at the probability that 2 of them go into remission. 3 of them, at least half of them go into remission. That all 4 of them, the probability that all 4 of them go into remission. So on and so forth. So this is what we can do with the binomial. Okay? First we have to be conscious of what's going on. So this combination we know is a way of choosing a distinct group of people out of how many possibilities we have of choosing a distinct number, say, of 3 out of 4, what we just looked at, times the probability of success raised to the power of the number of successes times the probability of failure raised to the number of people who failed. Okay, and we're going to step this through an example in just a second. If you want to follow this example, it's given on the page at the top of the page of 192. At the top of the page 192. Now, it's talking about tagged files. I don't think tagged files makes as much sense intuitively as cancer remission. Okay, so we're going to change the scenario, and we're talking about cancer research and the probability of success in an experimental cancer case. Okay? Now, the probability of success, we labeled that as P earlier, is 0.1. The probability of success is 0.1, meaning the probability of failure would be 0.9. We have 4 patients who are independent observations. They're not related, and they're all received. They all have the same type of cancer, and they're all receiving the same type of treatment. Yes. Now, the probability of success is 0.1. I'm looking right now at the probability that 3 go into remission. So I'm going to change this piece of x. I want to look at piece of 3. Probability that 3 of my patients go into remission. Now, it's the same. It doesn't matter. I'm not looking at, I don't care. Of course I do care, but I don't care what 3. I don't care what order they're in. I don't care if it's first it's patient 1, 2, 3, or I don't care if it's patient 2 starts, then 1, then 3. I don't care the order. I just care that 3 of my patients go into remission. You'll see the same combination. Now, because we don't care what order they're in, we're choosing 3 out of 4. We have our combination here, times 0.1, that's my probability of success, that 3 go into remission, and 1 minus 0.1, or 0.9, that's my probability of failure. And you see that's raised to 4 minus 3. If you step it down and have it simplified, again, my combination, times 0.1 raised to the 3, times 0.9 raised to the 1. Step that down further, we know that this combination is 4. We have a possible 4 different groups of 3 that could go into remission, 4 distinct groups. And again, 0.1 raised to the 3 is just 0.1 times 0.1 times 0.1. 0.9 raised to the 1 is 0.9. When I multiply that all out, I get 0.0036.